Good morning, class. We are looking at Chapter 5, Polynomials and Rational Functions. Here's 5.2, Power Functions and Polynomial Functions. 5.3, Graphs of Polynomial Functions. So Chapter 5 is about polynomials and rational functions. The sections we're covering, 5.2, Power Functions and Polynomial Functions. 5.3, Graphs of Polynomial Functions. The objectives are identify power functions, identify end behavior of power functions, identify polynomial functions, identify degree and leading coefficient of polynomial functions. Also, recognize characteristics of graphs of the polynomial functions, use factoring to find zeros of a polynomial function, identify zeros and their multiplicities, determine end behavior, understand the relationship between degree and turning points, graph polynomial functions, use the IVT, intermediate value theorem. So reminding you of the quadratic function. A quadratic function is a function that can be written in the form of f of x equals ax squared plus bx plus c, real numbers a, b, and c, with a not being 0. This is known as the vertex format. F of x is a times x minus h squared plus k is a parabola in vertex format. Now, here's the vertex x coordinate minus b over 2a, and the y coordinate is f of minus b over 2a if you happen to have it in this format. In this format, it's h and k. By the way, if you plug in minus b over 2a, you can get 4ac minus b squared over 4a. But instead of memorizing this, just plug it in. And when A is positive, the parabola opens up. A is negative, the parabola opens down. Axis of symmetry, a line that divides a graph into two symmetrical halves. X equals minus b over 2a. When you find the vertex, the x coordinate, x equals that is your vertical axis of symmetry. X-intercepts, as always, you set y equal to 0. Y-intercept, you set x equal to 0. So if you go back to this one, you notice that when x is 0, y is c, that's why 0 is c. The domain is always all real numbers, but the range, it depends. If it opens up from the y coordinate of the vertex to infinity, if it opens down from negative infinity to the y coordinate of the vertex, those are the vertex. When it opens up, we have a minimum. When it opens down, we have a maximum for the function. So those are the vertex. Now, 5.2, power functions and polynomial functions. 5.3, graphs of polynomial functions. Polynomial functions are in the following format. P of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0, where a sub n can't be 0. N is a whole number. The set of whole numbers, 0, 1, 2 to infinity. So that's the definition of a polynomial. Domain is all real numbers, minus infinity to positive infinity. The leading coefficient, these are called a sub n minus 1, all the way to a sub 0 are coefficients. A sub n is called the leading coefficient, and it can't be 0. And this is called leading term. The degree of the polynomial is n. Graph is smooth and continuous. Examples, a polynomial of degree 1. We are familiar with that. P of x equals mx plus b is a linear function. A polynomial of degree 2, P of x equals ax squared plus bx plus c is a quadratic function. So a warm-up example, P of x is given as 2x to the power of 6 minus x to the power of 4 plus 2/5 x cubed minus 2. By the way, you notice it's in Descending order, meaning the powers, the exponents on x, they go down. That's called descending order. So this is the leading term. Leading term. What is the degree? The exponent on that, the degree is 6. Is the function a polynomial function? If so, what is its degree? Let's start with the first one. You have to write it in descending order, or you just have to notice this is the leading term. So I'm going to write it as leading term. Let's use LT for short. And therefore the degree is 8. This is a rational function. Remember, the format is such that the exponents are whole numbers and you can't be dividing by anything. This one, yes, the degree is 0 because it's a linear function which is a horizontal line. So just for the sake of argument, nobody's going to write it that way, but you could rewrite this as 5x to the power of 0. You don't have to do that. You should recognize a constant. Y equals a constant, h of x equals a constant is a horizontal line. This one, the problem is this. It is also a rational function here. This one, the degree is 2 because if you were to multiply them out, what matters is the leading term is x squared, even if you don't write the rest, even if you said, okay, it doesn't matter what the rest is. As long as you write the leading term, and of course, in descending order, every piece follows the being a polynomial. The degree is 2, and yes. But if you were to write it out completely, then we could write -3 and +2. They add up to -1, so minus x. And then their product is -6. And as I mentioned, the problem here, okay, so this is not a polynomial, rather it's a rational function because this in essence is 4 over x, everybody. And the last one, part F, this is your leading term. Again, let's go with LT, leading term, and the degree is 3. Degree 3. All right, graphs of quadratic functions, parabolas are in the form of y equals ax squared. If a is positive, it opens up. Negative, it opens down, looking like this, opening up. Notice in this case, a is 1, which is positive 1. In this case, a is -2. So that's how quadratic functions look like. Cubic functions. When the degree is 3, we call it a cubic function. P of x equals x cubed plus bx squared plus cx plus d, and a can't be 0. And it will look like this one. When the degree is higher, y equals x to the power of 4 minus 3x squared plus x looks like that one. When it's even higher, looks like that one. For example, y equals 3x to the power of 5 minus 25x cubed plus 6x. You can use a graphing calculator, graph them to have an idea. So what does that tell us is that dealing with the power functions, we end up with the format f of x equals x to the power of a. A is a number, is a constant. A equals n, where n is a positive integer. So f of x equals x to the power of n. N is 1, 2, 3, and it continues indefinitely, or polynomials. They have only one term. For example, y equals x is a line through the origin with the slope being 0. Y equals x squared is a parabola. Okay, so we remember those. N is exponent. If it's even, f of x equals x to the power of n is an even function, and its graph is similar to the parabola y equals x squared. Looks similar to that. That is referring to finally the end behavior. If n is odd, f of x equals x to the power of n is an odd function, and its graph is similar to that of y equals x cubed. So graph of f of x equals x to the power of n. In the case of n being 1, 2, 3, 4, 5, they look something like this. Y equals x, n equals 1, y equals x squared, x equals 2, y equals x cubed, x equals 3. Now notice, in the case of y equals x to the power of 4, it's similar to y equals x squared. In the case of 5, both of them are even. You should notice that. That's the concept, the exponent. This one, x to the power of 5, is similar to x cubed. And that's the idea that is discussed here. So general shape. Remember, if you want to graph them, you need more details, but you should have an idea roughly how the graph looks like for elementary basic functions. As n increases, when the exponent gets larger and larger, the graph of y equals x to the power of n becomes flatter near 0 and steeper when absolute value of x is larger than 1. If x is small, then x squared is smaller. X cubed is even smaller. X to the power of 4 is smaller still, and so on. That's the reason for it. So the larger the absolute value, the faster they grow. That's why if you look at this one, if it's going slowly, it becomes faster. That's the idea is discussed here. And this is comparing various functions with n being even, x squared, y equals x squared, y equals x to the power of 4, y equals x to the power of 6. Notice they, on the right side specifically, you notice that they jump up faster, they increase faster. And this is y equals x cubed here versus y equals x to the power of 5. Graph the polynomial functions by transformation. F of x equals 1 minus x to the power of 5. And we start with the basic function, y equals x to the power of 5, similar to y equals x cubed. Doesn't have to be perfect. It looks something like that. So we're going to start with y equals x to the power of 5, then minus x to the power of 5. That means we multiplied by negative. That means it reflects about the x-axis. So this flips over. So this part goes up, this part goes down. Now, one thing I want to make a point of, we are multiplying by -1, and it's reflecting with respect to the x-axis. However, y equals x to the power of 3 or x to the power of 5 or x to the power of 7. Whether you reflected about the X or the Y axis, they do the same thing. Okay, because so this is now y equals negative x to the power of 5. But if I said minus x to the power of 5, also I get minus x to the power of 5. Because of that, again, what we are doing, we put the negative in front of x to the power of 5, so it's reflection with respect to x. But if you reflect it with respect to y, also it will look absolutely the same. Then the effect of 1 is that we bring it up by 1 unit. So notice the 0, 0 remains, 1, 1 becomes negative 1, 1, negative 1, negative 1 becomes positive 1, negative 1. Now we're going to take it up by 1 unit. When we take this up by 1 unit, the x coordinates remain the same. The y coordinates add 1. This becomes 2, this becomes 1, this becomes 0. Look at those. So we are going to add 1, shift up 1 unit. And this is what it looks like. Look at those 3 points. You can pick up a few points just to see what happens to them. One half x minus 1 to the power of 4. It looks like times 4, but this is to the power of 4, everybody. So you start with x to the power of 4. Looking almost like y equals x squared. And again, easy points 0, 0, 1, 1, negative 1. We can use x minus 1, which means we are going to replace the x with x minus 1, which means we are going to shift it to the right by 1 unit. When we shift it to the right, the y coordinates of these 3 points remain the same, but the x coordinates, they go up by 1. The y so this one, negative 1, go up by 1 becomes 0. This 0 becomes 1. This 1 becomes 2. So the x coordinates, we are adding 1. And finally, we're going to multiply by 1/2, which is compression by a factor of 1/2, which means what happens to the x coordinate is nothing. The y coordinates, they get multiplied by 1/2. So this becomes 1/2. 0 doesn't change. This becomes 1/2 as well. And it becomes wider in essence. So this is wider than this. That's the transformation you use. Theorem behavior near 0, multiplicity. The zeros of a polynomial f of x are the solutions of the equation f of x equals 0. Equivalently, number 1, each real 0 is an x-intercept of the graph of f. F of c equals 0, there is at least one 0c, and hence by the factor theorem, f of x has a factor of the form x minus c. Number 3c is a solution of the equation f of x equals 0. If a factor x minus c occurs m times in the factorization, then c is a 0 of multiplicity m of the polynomial f of x, or a root of multiplicity m of the equation f of x equals 0. If c is a real 0 of f of x of multiplicity m, then f of x has the factor x minus c to the power of m, and the graph of f has an x-intercept c. If m is odd, then x minus c to the power of m changes sign as x intersects through c, and hence the graph of f crosses the x-axis at c0. For example, y equals x to the power of 5 or x to the power of 3 or x to the power of 7. It crosses because it does change sign, x minus c to the power of m. And if m is even, then x minus c to the power of m does not change sign at c, and hence the graph of f does not cross the x-axis at c0. For example, y equals x to the power of 4 at that given point, because it's x and the exponent is 4, it can't cross because the sign on both sides of the intercept remain the same. Identify the real zeros of a polynomial function and their multiplicity. Here's a graph of a polynomial function, smooth, continuous. This cannot be the graph of a polynomial because it's not smooth. We have sharp corners. It's a corner cusp. It's a discontinuous point here and here. So it has to be smooth and continuous. So here's the graph of a polynomial function. Of course, everything here is below the x-axis. Everything there is above the x-axis. This is where the function crosses the x-axis, which means this intercept, for example, whatever this number is, x minus this number to the power of n, that must be odd, whereas this one must be even because it can't cross. It crosses here, it crosses here too. Turning points. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. If the graph of a polynomial function has n minus 1 turning points, then the degree of f is at least n. So I want to make sure we understand this concept. So we know the degree is n, then we have n minus 1 turning points. For example, if n is 5, we can have maximum of 4 turns in the graph. So this is one turn, this is another one, this is another one, this is another one. But if you know the number of turns, at least you add 1 to it, at least for the degree. Finding finding a polynomial from its zeros. Find a polynomial of degree 3 whose zeros are -4, -2, and 3. So how do you set this up? You say f of x or p of x or g of x, it doesn't matter, equals. Now, since we want a polynomial, we don't know what would be the leading coefficient. We put something like a, but this gives you x plus 4. This gives you x plus 2, and this gives you x minus 3. Why a? Because there are infinitely many polynomials that they have these zeros. And if you change the leading coefficient, of course, multiplying by the entire thing, the graph shape changes a little bit, but the zeros remain the same. So you're going to multiply this 3. I'm going to leave it for you to do that. And you end up with a times x cubed plus 3x squared minus 10x minus 24. Everybody can do the multiplication. So given x minus r to the power of m is a factor of a polynomial, and x minus r to the power of m plus 1 is not a factor of f, R is called a zero of multiplicity M. So if it repeats however many times, let's say it repeats 4 times, then we say the multiplicity is 4, but not 4 plus 1, 5. That's the idea. So given the polynomial, list the zeros and their multiplicities. This has no bearing, it's just the A on 0. So that becomes the leading coefficient. So look at this one. This says 2 is a 0. What is the exponent on this parentheses? Missing, that means the exponent is 1. So the multiplicity is 1. 2 is a 0 of multiplicity 1. The factor x minus 2 has exponent 1. This one, if you set this equal to 0, x equals negative 1. What is the multiplicity? 3. Negative 1 is a 0 of multiplicity 3. The factor x plus 1 has exponent of 3. Finally, this one, you set this equal to 0, x becomes 3. And 3 has a multiplicity of 4. 3 is a 0 of multiplicity 4. The factor x minus 3 has exponent of 4. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0 look like y equals a sub n x to the power of n. The leading term looks like its leading term. That means the end behavior looks like that. So for example, in this case, I hope you see that as x goes to infinity, f of x goes to infinity also, meaning as x gets larger, y gets larger. This one, as x goes to negative infinity, then y is still going up. That is because the leading term has an exponent which is even. So n is larger than or equal to 2, and it's even. And how do we know it's larger than or equal to 2? Because it has 1, 2, 3 terms. So it must be 4 or larger. This one is the same as this one, but the leading coefficient is negative. Okay, so this number is negative. These two, the only difference that this number is positive or negative. And so as x gets larger, when x goes to infinity, y goes down to negative infinity. When x goes to negative infinity, y, remember, y or f of x, they both go to negative infinity. And of course, n is larger than or equal to 2, the same reasoning that I mentioned. In this case, n 1 and 2 terms, so n is larger than or equal to 3, and the reason it's odd looks like the end behavior looks like the end behavior of x cubed. X gets larger, so does y. Both of them go to infinity. X gets smaller, so does y. Both of them go to negative infinity. And this is the notation, by the way, as x approaches infinity. That's the concept known as a limit. Later on, we'll discuss this with more details in calculus. So f of x is approaching infinity. That's the meaning of it. And this one looks like minus x cubed. I'm talking about the end behavior. So this one is the first and the third quadrant. This one is the second and fourth quadrant. As x goes to negative infinity, we go this way, y blows up to infinity. In this case, when x goes to infinity and gets larger this way, f of x gets smaller, f of x over y. So that's the idea of the end behavior. The end behavior similar to y equals x squared. The end behavior similar to y equals negative x squared. This one similar to x cubed. This one similar to minus x cubed. graphing polynomials using its intercepts and end behavior. Later on, of course, when we add calculus, we have a better idea as to what happens to them as far as finding max, mean, intervals of increasing, decreasing, and so forth. So basically, it's very easy to see that this is a 0. So x-intercepts happen at set this equal to 0. And it happens at -1 and +2. So we have -1, 0, 2, 0. So we found 2 x-intercepts. And as far as the multiplicity is concerned, this doesn't have any exponent. That means exponent is 1. So this one has a multiplicity 1. But 2 has a multiplicity 2 because the exponent is 2. I'm going to use m for multiplicity. So we're going to let m represent the multiplicity. So when we say m, it is the multiplicity. Multiplicity 1, multiplicity 2. And so what are the intercepts? We have those 2 intercepts. What about the y-intercept? If you go back to this format, it's easier. X is 0, so it becomes 4. In other words, 0, 4. So we have all the intercepts. What about the end behavior? The end behavior, look at the leading term. The end behavior looks like x cubed, which means the first and the third quadrant. That is the concept of an end behavior. So let's make up a summary table for what we have so far. So we have the x-intercept at -1, 0. We have the y-intercept at 0, 4. Well, later on, you'll see that in actually calculus, y, we have this arrow. This represents the max. It can't cross it. You don't have to worry about it at this point. We have another x-intercept at 2, 0. This is an extra point class. If you plug in 1, you do get 2, an extra point. Now, here's what's interesting. I'm going to put an arrow here. This is what we use in calculus. Remember, we said the multiplicity is 2 for 2, 0. That means when it hits it, it can't cross it. So even if you don't have this point, you don't know what happens here. If you were to graph this, you would say, okay, here's the end behavior. It's going to hit this point, but it can't cross, has to come back up. Let's say I don't know how it goes. Let's go, it goes up and comes down back at some point. But as it hits this one, it has to go through the point, or it may go like this and come down, or it may go like this and then come down. So we may not know when it peaks, not using calculus, and that's fine. But we know the end behavior, we know the intercepts, we know the multiplicity, and we should be able to graph this easily. and is an extra point. 3 comma 4 is an extra point class. So the graph is what you see here. So this is with a little bit more details. All right, graphing polynomial using its intercepts and end behavior. Well, x-intercept, if you set this equal to 0, one of them is 0, x equals 0 and x equals 3. So we have 0, 0 and 3, 0, where this one has a multiplicity 1, and this one, 3, 0, has a multiplicity 2. So 0 is the 0 of multiplicity 1. The exponent and the factor is 1. Remember, when there's no exponent, that means the exponent is 1. And this one, m equals 2. The exponent and the factor x minus 3 is 2. So it's fairly easy to distinguish between the two, everybody. What about the end behavior? What you need to know, if you multiply them out, it's x cubed. You don't even have to know the rest of them. This is your leading term. Although you can say x minus 3 squared is x squared plus 6x minus 6x plus 9. You can do this. You can raise this to the power and you get x squared minus 6x plus 9 and then apply the x. But we are interested in the leading term, which means right away, this is the meaning of the end behavior. Okay, looks like y equals x cubed. So you plot the points 0, 0, 3, 0. By the way, 0, 0 is both the x and y-intercept. It happened to be both of them, okay? So the end behavior looks like x cubed. Here's 0, 0. Here's 3, 0. And I'm going to put this arrow that I like. So right away, what it means is that it comes down, it hits this point, but it can't cross because the multiplicity is 2. It has to go back up. How far it goes, we don't know, but it has to come back down. It hits this x-intercept, but it continues. So it looks something like that. You can always add a couple more points. And then, for example, 1. If I put 1 here, let me erase this. If I put 1 here, 1 minus 3 is negative 2 squared is 4. So 1, 4, and I'll put them all together. So the point being, you can always add a couple of points. You know the end behavior. You know the behavior near an x-intercept. If the y-intercept is different than those, find that. And then if need be a couple more points, you have the graph, you're done. Identifying if the graph represents a polynomial function, indicate the number of zeros and degrees. Part A. As you look at the graph, you notice this is not a polynomial function. Why is that? Discontinuous. The function is discontinuous. CTS, short for continuous. This one, yes, the graph is a polynomial because it's smooth and it's continuous. What about the zeros? There's a zero at -2. There is a zero at 1. There is a zero at 2. So 3 zeros. One and two turning points. The degree is 3 or larger. So it has zeros at -2, +1, +2. There are two turning points. The degree must be 3 or larger. What about this one? No. Why not? Sharp corner. It has a sharp corner. It's not smooth. Is it continuous? Yes. But it can't be a polynomial function. If you look at the last one, seems to be smooth and continuous. Yes, the graph represents a polynomial function. It has a zero at this point, -2, and at this point, +1, and it has 1, 2, 3. So 1, 2, 3 turning points. Therefore, the degree must be at least 4. So one more time. It has zeros at -2 and +1. There are 1, 2, 3. One short way of looking at it would be peaks and valleys. Peak, valley, peak. Okay, max, mean, max. There are 3 of them, so the degree must be at least 3 plus 1 or 4. Identifying the graph of a polynomial function, which graph could be the graph of f of x equals x to the power of 4 plus 5x cubed plus 5x squared minus 5x minus 6. So that's what we want to figure out, everybody. Notice that whenever you have a function in this format, your y-intercept is the constant. F of 0 is -6, so the y-intercept is at 0, -6. So 0, -6, when we look at this one, does it have a y-intercept? Yes. Where is that? It's 0 and some positive value. This one has a negative value. This one has a negative. I'm looking at just the y-intercept. So the first one is out. Then I look at the leading term. Leading term. The degree is 4. And 4 minus 1 is 3. Maximum, we have 4 minus 1 or 3 turning points. This has 1, 2, 3, 4, 5. This is out. This has too many turning points. The end behavior for x to the power of 4 it's going to look like x squared. So the end behavior must be the end behavior of x to the power of 4. And x to the power of 4 looks like x squared, meaning this is the end behavior. Okay, everybody? Therefore, this one is out. And so the answer must be A. I hope everybody is clear as to what I'm saying here. It should be pretty straightforward, everybody. I'm going to quickly recap to make sure everybody's fine with that. First, we look at the y-intercept. That is a very easy point to look at. And because the y-intercept is negative, and all of them have a negative y-intercept except this one is out. Then we look at the degree, it gives us the number of turning points. And this has too many turning points, this is out. Finally, the end behavior, the leading term tells us the x to the power of 4 will take over, and x to the power of 4 or x to the power of any even exponent will look like x squared. This is the end behavior, okay? So this is fine. If it was minus x to the power of 4, this would be the answer, but it's not, and it's out. So I hope you see how you come up with the answer. Write a polynomial function from its graph. So we start with the intercepts. The first one we notice, x-intercept at -2, 0. So, or simply -2. And because it crosses, it doesn't cross, it bounces back, the multiplicity is even. The next one is 0. The multiplicity is odd. The next one is 2. Both of them, the multiplicity is odd. Because the graph crosses the x-axis right then and there in both cases. Right here it crosses, right here it crosses. And then we have 1, 2, 3, again, turning points or peaks and valleys or max and mean. 1, 2, 3. There are 3 turning points. N must be at least 3 plus 1. So must be at least 3 plus 1 or 4. We are going to write this as y or f of x equals a times. This one gives us x. This one gives us x minus 2. This one gives us x plus 2. But m is 2. So again, 0 gives us x. 2 gives us x minus 2. -2 gives us x plus 2. And so this one gives us that. M is even, we take it to be 2. All we have to do, pick up a pair and plug in. They have given us this pair, -1, 6. So into this function, x is replaced by -1 and f of x or y is replaced by 6. -1, 6. That's an easy point that is given, everybody. Plug in. -3, +1. And I hope you notice that when you square it, this is still 1. And so 1 times And negative 3 is negative 3 times negative 1 is positive 3h, so 6 plus 3a divided by 3a becomes 2. And replace this, and the function is 2x times x minus 2 times x plus 2 squared. Now, if they want you to multiply them out, you do that. If factored format is good enough, so be it. So it depends on how they ask you. Example 11, analyze the graph of a polynomial function. F of x is given as 2x minus 1 times 2x plus 1 times x plus 3 squared. If you multiply them out, you get 4x to the power of 4 plus 24x cubed plus 35x squared minus 6x minus 9. This is more important to us in order to graph them because we want to look at a bunch of stuff. And I have the steps that we want to take here, everybody. For example, we want to look at the end behavior. That's why this is handy. Okay. Notice n is a 4. A happened to be positive. So the end behavior looks like x to the power of 4, or more importantly, x squared. So n is 4, this number, not this one. It so happened a is 4 also. So this is n a sub n. Okay. And because this is even, looks like x to the power of 4. And of course, we are familiar with x squared, which right away means, just for the sake of argument, means this. That's the end behavior. All right. The intercepts. This, if you set it equal to 0, gives you 1/2, comma 0. This, negative 1/2, comma 0. This, negative 3, comma 0. So those are easy intercepts. And from here, everybody, 0 and negative 9 is the y-intercept. Now, what about the multiplicity of these zeros? Exponent 1, multiplicity 1, crosses the x-axis. Same thing here. No exponent, that means multiplicity 1, it crosses the x-axis. The last one, minus 3, 0, multiplicity is 2, doesn't cross the x-axis. How about the maximum number of turning points? Well, n is 4. 4 minus 1, n minus 1. So maximum could be 3 turning points. So if we put all of this together, okay, so this is the end behavior. Those are the intercepts, everybody. And notice crosses here, but at negative 3, 0 doesn't cross. And here's your y-intercept. All you have to do is just graph those 4 points. And at negative 3, notice that it's not going to cross. That's why I like to put this arrow that we use in calculus. And it shows that it crosses it. Okay, the graph crosses at this point, and this is the y-intercept. It doesn't cross here. Okay, the graph touches the x-axis at that point. Putting them all together, the graph will look like this. So you should have a rough sketch as to how the graph looks like. Analyze the graph of a polynomial function. Form a polynomial whose degree and zeros are given. Don't expand. Degree is 3, zeros are -2, 0, 4. Let's look at the first one. So this gives you x plus, this gives you x, this gives you x plus 2, this gives you x minus 4. And remember what they want. They say form a polynomial. I can put any number here. I chose not to. If you don't put anything, it's 1. But if you pick any number and you put it here, it's absolutely fine. You put 5 or -2 or 8. It doesn't say anything else. All it says, these are the intercepts. So 0 gives you x, minus 2 gives you x plus 2, and 4 gives you x minus 4. Now, part B, 0 of -2 with multiplicity 3. So this is x plus 2 cubed. And then 0 of 1, multiplicity 1, x minus 1. So f of x is simply x plus 2 cubed because of multiplicity 3. And then x minus 1 and multiplicity 1. What about the graph? Find a polynomial function from the graph shown. From the graph shown. Well, we have 1, 2, 3 x-intercepts. This is one of them. This is another one. This is another one. So this is located at -2 with multiplicity 1 because it crosses. This is located at 0 with a multiplicity 1 or odd because it crosses. This one, 1, 2, 3, x equals 3, if you will, okay, which results in x minus 3. And this has a multiplicity even because it doesn't cross, it bounces back, it touches it and bounces back. So for this one, we're going to write x. For this one, so let me write the numbers. So I want to make sure we can see those. So this is 0, so we get x. This is -2, we get x plus 2. This is 3, we get x minus 3. And for the last one, since it crosses x minus 3 squared, so f of x. So multiplicity is 1 here, 2 here, okay? Yeah, actually, now it's clean. You can see f of x is x times x plus 2, and then x minus 3 has a multiplicity 2. And I hope you see that you have 1, 2, 3 turning points, and the degree must be at least 4. And this has degree 1, this has degree 1, this has degree 2. So the degrees, they add up to 4 when you do the math. So it becomes pretty obvious as to what's the answer. Use IVT, intermediate value theorem. If f of x is a polynomial function or any continuous function, and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. I want to make sure we understand the concept. So we have a continuous function. There is no break. If it's a continuous function, and the bottom has the y coordinate f of a, the top has f of b, every number between f of a and f of b must be covered. That's the concept. Even if both of them are positive, it doesn't matter. The point is everything from here to here must be covered because this is a continuous scale. So if one of them is negative, like f of a because it's below the x-axis, and one of them, like f of b, is positive, then it has to contain, this will contain a zero. Then that's what it's referring to. So it has to cross the x-axis at some point, give us the root, the zero. That's the idea. So show f of x equals x to the power of 5 minus x cubed minus 1 has a zero between 1 and 2. So if they say specific numbers, then you plug in those specific numbers. If they say show that there is a zero somewhere, then it's a trial and error to figure out at some point the function must have a functional value which is positive and at some point is negative. So for example, f of 1, f of x is continuous, and by intermediate value theorem, it has to have at least 1 0 in between. If what? Let's look at it to find out why this would be the case, and that's extremely important. So number 1, let's find f of 1. F of 1 is 1 to the power of 5 minus 1 cubed minus 1. And I hope you see that it's negative when it's negative. So f of 1 ends up being a negative value. We are interested in the sign. And then f of 2 is a 2. Let me use a different color. To the power of 5 minus 2 cubed minus 1. 2 to the power of 5, 32, minus 8, 24, minus 1, 23, and 23 is positive. Again, it doesn't matter what values. We are interested in negative versus positive because f of 1 is negative. So in essence, it becomes like this. F of 1 equals negative 1 less than f of 2 equals 23. There must be something in between f of some point x that must be 0 somewhere. Maybe I should use f of c because 0 is between the two. According to the IVT, f of x is continuous, and by IVT, it has at least 1 0 in between. Show p of x equals x cubed minus 2x squared minus x plus 1 has a 0 between 2 and 3. They have given us a specific points. So basically, we are going to plug in 2 and 3. And we hope one of them gives us negative, one of them gives us positive. So p of 2, that means 2 cubed minus 2 times 2 squared minus 2 plus 1. So this is 8. This is 4 times 2 is 8. 8 minus 8. And it becomes negative 1. Let's plug in 3. We get 3 cubed minus 2 times 3 squared minus 3 plus 1. This is 27. 3 squared is 9 times negative 2 minus 18 minus 3 plus 1, we get 7. So what are we looking for? We are looking to see if there's a 0 in between, and clearly there must be 1. Because you're dealing with a polynomial function of degree 4, which is a continuous function. By IVT, it has to have 1 0 in between the two numbers. So that's the concept. What I want to also discuss the table feature in TI-84, because if you want to evaluate this at many values, or the numbers get involved, this might be tedious. So the process is to use the graphing calculator and a table value. So you click on Y and put in the information you want. The function in this case is x cubed minus 2x squared minus x plus 1. So you put it here by clicking Y. It gives you this. And of course, if you click on the graph, it brings up the graph, looks like that. And from the graph, you can guesstimate where the x-intercept is. They just don't want the x-intercept. We have seen how to find the x-intercept using a graphing calculator. I want to discuss the table if you want to evaluate the function at different values. So creating a numerical table for a function or table, you can go to this video class. I'll put it up. It gives you the details. On YouTube, you can go to YouTube, this URL, or press Y and enter the function. So press Y and enter the function. Okay, so the Y, put in the function. And to view the table, go to second table. Okay, and I'm explaining how to set up your table. Go to second table, set view the table, go to second table, so add a second function into Y, and so on and so forth. So take a look at what we have here. Second table and second. This is the table set. This is the table. With the table, you can see this. It uses integers for the x, and for the y, whatever you put in the y1, and it evaluates it for you. But if you go to table set, you can say you want to start from a different point, and instead of, normally this is 1, if you keep it as it was, automatically it does this one. But if you make this change, again, you tell it what is your starting point, okay? Second table set, it may be hard to see here. And then you can say, okay, I want to add just 1 or 0.1 or 0.01 or 0.001, and it does the calculation for you. The advantage of using the table is, again, if the numbers are easy, like 2 and 3, we can do it. But if it gets involved, it's very difficult. So the purpose of that was to use numbers that are pretty difficult to do. So we let the computer, in this case, the graphing calculator, do it for us. I just wanted you to see that. If we make it larger, we notice, for example, between these two numbers, notice this is negative, everybody. 2.246 results in some negative value, negative 0.005. But the next one, 2.247, gives us positive value, 1.1 e minus 4. That's a scientific notation. That means 1.1 times 10 to the power of negative 4, which means, therefore, the 0 lies between these two numbers, 2.246 and 2.247, since there's a sign change in the function values. Why did we pick those numbers? I'm doing it on purpose to make a point, meaning how to use a table, how to create a numerical table, and how to use the table function using a graphing calculator.